Hello everyone, this is the second video on fluid statics. So the main problem we want to answer by the end of the video is in red right here. So imagine we had ice, an ice cube floating in water, and we want to be able to answer the question, when the ice cube melts, what will happen to the water level? Should it rise, fall, or remain the same? So to answer that, we're going to need an equation for buoyancy and then see how it plays into that problem. So before buoyancy and Archimedes' principle, we want to talk about a few basic things first. So even before Pascal's principle, I want to mention a few things from section 14.3. So first of all, your book talks about gauge pressure. So when you fill up air in your car tire, if you want to fill it up to 32 psi, pounds per square inch, that measurement is how much pressure should be in your tires above atmospheric pressure. So there's a bunch of units of pressure that your book goes over in a couple pages from there. So there's this psi at the bottom of the table. So 14.7 psi is 1 atm. There's a bunch of conversions, so 5 different ways of writing 1 atm. So when you have 32 psi in your car, it's a little over 2 atmospheres of gauge pressure, but in terms of absolute pressure, that's a little over 3. Right? It's just the difference. It's how much above atmospheric pressure. So keep that in mind, when you see these readings of pressure outside of the textbook. Okay, so one other thing I want to point out, another unit of pressure is millimeters of mercury. This 760 mm of Hg. So I want to talk about what that means. So a barometer is a pressure measuring device. So if you have a tube full of liquid, and it looks like this thing's blue right here, so we'll just assume that's water. If you have that tube of water, you turn it over and put it into that dish of water. When things come to equilibrium, so first of all, you have vacuum inside the tube because there was no air in there, right? So if the water level goes down, it's just vacuum in there. So it settles until points 1 and 2 are at the same pressure. Point 1 is at atmospheric pressure because it's open to the atmosphere, and point 2 has a pressure due to the column of liquid above it. As we saw last time, the pressure at point 2 would be 0, the pressure inside the vacuum, plus rho g times h would be the depth inside that fluid. So if you set rho g h equal to 1 atmosphere, make sure it's in SI units, and you solve for h, you'll get about 10 meters, or about 33 feet. So if you're using water to measure pressure, you would need a column of water 33 feet, or 10 meters high, which is very, very high. But if you use something with a greater mass density, then that height won't be as big. So mercury actually has a pretty big density. It doesn't require a full 10 meters. It requires less than a meter. Actually, 760 millimeters for 1 atm. So this is just a practical way of measuring pressure. So millimeters of Hg just refers to the actual physical measurement that people are making. Okay, so you can take a look at some of the other units. But yeah, we're going to mainly stick with the 101.3 kilopascals, because that'll be our SI units, and then that's equal to 1 atm. We're basically going to ignore the other ones. Okay, hydraulic lift. So this is kind of a surprising and useful thing here. So I drew a hydraulic lift right here. So I have a thin column and a thick column. I have 2 platforms just so we can put things on top of them. So these things are open to the atmosphere. So right now, if the platform, so we're going to imagine it's a light but very rigid platform. So by light platform, I mean the pressure here is equal to the pressure right above the platform, which is open to atmospheric pressure. So without anything on the platforms, the big one or the little one, we're at 1 atmosphere of pressure. at both of those 2 points. But now imagine that you put a car right here on the big platform. You're going to see just how terrible my drawing is. It's my car. So we have a car on the platform. So you can imagine if we put the car on the platform, this side is going to want to go up, right? So we want to be able to see by how much should that go up. So to answer that question of how much it needs to go up, or how much we would need to apply a force down here to support the car, we're going to need Pascal's principle. So what Pascal's principle says is that whatever increase in pressure that the fluid is going to feel, and the fluid right here, just below the platform, is going to feel an increase in pressure. It's going to go from atmospheric pressure to the weight of the car divided by area. So let me start to write down some numbers here. So this is A1 and A2, and we have m car, g, as the weight of the car. Well, there's an extra force. Maybe I should use a different color. There's an extra force right here on this layer of water that's equal to mg, m car g. So the pressure there is going to be m car g over A2. So the increase in pressure, so we'll write delta P, is m car, I'll just use a C from now on, m car g divided by the area. Okay, that's the increase in pressure just below the platform. So what Pascal's principle says is that increase in pressure, this delta P, is actually felt throughout the whole fluid. So everywhere inside this fluid is going to feel that same increase in pressure instantaneously. So any increase in pressure is felt everywhere throughout the fluid. And this applies to incompressible fluids. So something like water is very, very hard to squeeze, to change the volume of. You require extraordinarily high pressures to do that. So the volume of the water isn't going to change. So it's incompressible fluid. Okay, so what that means is, so now if I focus on this platform right here, what that means is that the pressure just underneath this platform, so this point right here, is at a higher pressure now relative to this point. So maybe I should label these. This will be P0 and P1. So now pressure P1 is greater by this amount, mcg over A2, greater relative to P0. And so pushing on this platform right here, so we'll call it the small platform. So on the small platform, it'll be pushed upwards. So there are a couple things we could do. We could increase the pressure on this top side by just pushing down on it. So let's say we want to apply a force, have a F applied, so that the small platform doesn't feel any net force. How big should that applied force be? Well, so F applied divided by the area there, A1, is going to be the increase in pressure relative to P0, and this is going to be equal to, we want to set it equal to the pressure on the other side. So this is one way of looking at it in terms of pressures. In terms of forces, so this is pressure. In terms of forces, it's the same sort of analysis. So F applied plus P0 A1. These are so I'm basically just taking the pressure equation and multiplying by A1. And this way of looking at it, it's the two forces that are pushing down. It's the applied force and then the atmospheric pressure pushing down on the small platform. And then what's pushing up is P1, the pressure on the other side, times A1 to turn it into a force. So to solve for F applied should be equal to, looks like it's P, so A1 times P1 minus P naught, and that's exactly the delta P we have right here. So I can go ahead and plug in mcg over A2. Okay. So you'll notice that mcg is the weight of the car. So this is something like, I don't know, 3,000 pounds for a mid-sized car. So if that ratio A1 over A2 is really, really small, so if I have a really thin cylinder on the left and a really thick one on the right there, I actually don't need to push very hard on the left in order to support the weight of the car. This is the principle behind a hydraulic lift. So it actually doesn't require a huge force to lift that car. So with your little pinky finger, you can lift up a whole car. Of course, the more, so you might say, well, you know, there's something weird about that, right? I can't really lift a car. Notice how you would have to push a really long distance in order to lift the car up just by a little bit, because the areas are so different. So you can lift a car, but you're not violating conservation of energy. If you actually trace the work, if you do the force times the distance on the left, that's equal to the force times the distance on the right. So you're not violating conservation of energy. So this is one way you could balance the car. The other way is for the fluid level to go up on the left. So the amount that it would have to go up by is that amount that would lead to an increase in pressure. So the height difference would have to lead to a pressure difference that's equal to mcg over A2. This pressure difference on the right here. Okay, so that's another way that you can restore equilibrium there. So this is really useful for, it's not just hydraulic lifts, it's the brakes in your car operate on a similar principle. You have to push relatively light in order to get a pretty big force to stop your car. So you have to push more on your brake pedal than the brake calipers actually move. Okay, so that was the first one. First thing we want to cover. Buoyancy now. Okay, so we mentioned in the last video that if you have, so first I was just looking at some water right here. So the only thing I'm going to do differently is, rather than water right here, I'm going to have some object, maybe a rock. So remember last video we just looked at like a cube of water, and we said that there was less pressure right here than pushing right here, and that's why you could support the weight of the object, right? So what Archimedes' principle allows us to do is we're just going to have one single equation for the total buoyant force. So overall, the overall effect, because of smaller pressures up on the top versus on the bottom, the overall effect is to supply a buoyant force. So there's the mg for the rock, the gravitational weight of whatever object is in the fluid, and then there's a buoyant force. So we need an equation for this. So Archimedes' principle says that F buoyant, the upward force from the object being submersed in a liquid, is equal to, so it's going to be the product of three things. So rho fluid, G times V displaced. So I'm going to have to explain those three terms. Okay. So rho fluid. This is the surrounding fluid. So notice how this is not the density of the rock, but this is the density of the surrounding fluid right here. So this is rho fluid. The density of the rock actually doesn't matter for that rho part. Okay, so this is the surrounding fluid, density of the surrounding fluid. So remember, for water, that's 1,000 kilograms per cubic meter. G is the 9.8 meters per second squared. I think you're comfortable with that one. V displaced is the volume of fluid displaced. So sometimes this is equal to the volume of the object, sometimes it's not. So if an object is fully submerged, like in the picture with this rock right here, it is fully submerged. It's completely under the water level, the fluid level. Then V displaced is equal to the object's volume. So V displaced can equal, so it's sometimes, so let me put a equal sign but with a warning here, sometimes, equal to the volume of the object that's submerged. Okay. So, but not always. Okay. So, for a rock, well, actually, I want to go back. So at this point, we're able to answer this primary question right here with the ice floating in water. So now I want to point this out because this is where the volume submerged is not equal to the volume of the object. So right here in this picture, this is the amount of the ice cube that's submerged. So this is the volume that's going to appear in Archimedes' principle, not the whole volume of the ice cube, but just the amount that's under the water line. So again, if something's fully submerged, you can use the volume of the object, but if it's floating, then you have to take the amount that's underneath the water line. Okay, so let's go to this ice cube problem and figure out just what happens. Okay, so first let's write down some equations to figure out what the volume displaced is. And then afterward, we'll figure out, after the ice cube melts, we'll figure out how much volume it takes up, how much volume of water it is. Okay, so the ice cube is in equilibrium, and so these two forces are going to be equal. So there's the mass of this ice cube. And for reasons you'll see later, I'll call it MH2OG. And then this upward force is going to cancel it because the ice cube is in equilibrium. So this buoyant force, F buoyant, which is rho of surrounding fluid, which in this case is water. So I'm going to go ahead and put a subscript W for the rho. Not the density of the ice cube, but the density of the surrounding fluid. Rho GV displaced. Okay, now setting the two forces equal, sum of the forces on the ice cube is equal to 0. So setting these two equal, we get rho GV displaced is equal to M H2O times G, or V displaced equal to mass times G divided by, oh sorry, I could cancel out the G's. There's a G on this side and a G on this side. So it's the mass of the water, or the H2O, the ice cube, divided by rho water. Okay, so this is how much volume. This isn't the volume of the ice cube. This is the volume underneath the water level. Right? It's this part in black right here. Right? Just that. Okay, so that's making the water level rise, right? If the ice cube wasn't in the water, if we were able to take the ice cube completely out of this thing and just hold it in our hand, the water level would go down by some amount, so that the volume going down was this. Okay, so now let's look at the ice cube melting. So ice melts. So that ice cube, so MH2O, which was equal to the mass of the ice cube, becomes here. It's MH2O. It's that same mass. It's just turned into water now. It's mass of water. Right? All three of these things are, so this, and this are all equal. It's just talking about, so before it was talking about the ice cube before it melted, and this is after. So how much volume does this ice cube take up? So it's going to melt. We want to figure out how much volume the melted ice cube takes up. So the volume of the H2O is mass divided by density. Mass of the H2O divided by the density of the H2O, which is now water. Right, see how the units work out? Mass divided by, and then density is mass per unit volume, gives you volume on the top. Right, mass, so this is just a rearranging of density equals mass per unit volume. But see how this is exactly the same? So this and this are equal. So the volume displaced is equal to the volume of water that the ice cube is going to turn into. So see how ice is less dense than water? It's part of it sticking out of the water level. When it melts, it's going to take up less space because water is more dense than ice. And it fills up exactly the amount of volume that it was taking up in the water. So the water level doesn't change. So we wrote out some equations to see why this works out, but actually we didn't need to write out anything. We could just look at the picture and say, well, the amount of volume that the ice is displacing is exactly equal to the weight of the ice cube. And that weight of the ice cube doesn't change after it melts. So it's going to take up the exact same amount of volume. Okay? So in class, we're going to look at some more complicated examples where you have someone on a boat and maybe you throw some rocks or some ice cubes off the boat and have them sink or float, and we'll look at the water level. But this is the sort of the way you want to analyze these problems.